Hello, my name is Lily Alterin, and today I'll be presenting to you Lab 2, Charge Tapes Revisited. Now, the purpose of this lab is to analyze and understand the charge and interactions between two pieces of charge tape. It's also to simulate the charge tape experiment using glow strip, and it is to compare the electric force from the previous point charge model of the tape system to a line of charges model of the tape system. Now, as a little preview of the results of this lab, the charged pieces of tapes repelled each other, thus they were deemed to be positively charged. In lab 1, the point charge was determined to be 4.24 e to the negative ninth coulombs, and the line charge of the tape was determined to be 1.25 e to the negative eighth coulombs. Now, as a little introduction, Newton's second law, also known as momentum principle, relates the total interactions to the changes of motion in the system. This is represented by this equation right here, F of net equals dp over dt, and it's also relating to the force of gravity, which only acts in the y direction as seen right here, and it's F equals ma, or with gravity's case, negative mg. And then for universal gravitation, now we're not using this exact formula in this lab today. We will be using the r's to find our positioning and our observance, and it is important to know how our r vectors and our original starting points and positions work. So if we were to find it, the r of the system minus the r of the source is how we find our r vector. Now Coulomb's law is the force of repulsion or attraction between two electric charges and is represented by this formula right here. K in that formula is Coulomb's constant, a given, which is 9 times 10 to the ninth power. Q1 is point charge 1, Q2 is point charge 2, and r is the distance between these two charges. Now, the modeling program I used for this experiment was WebPython, and just as a little note, some of the data used in this lab was calculated and derived from a previous lab, and right here to the right is just a picture of the charge tape system. Now the lab 1 results plus the experimental data. So the system was two pieces of tape and the water bottle and computer holding up the tape and the pen. And it can be seen by this little force of gravity right here. The force of gravity is pointing downwards in a negative y direction, while the force of the electric field is pointing in a positive y direction up. And as you can see, right here to the left was what I got from my computational data and modeled it found the charge as stated before to be 4.24 times 10 to negative 9 coulombs. And this is just a little image I generated with my code. And just for some constants we gained from this part of the lab, the length of the tape was 0.165 meters, the mass of the tape was 0.000165 kilograms, the distance between the two tapes when one began to float above the other was 0.01 meters, the magnitude of the gravitational force on the piece of tape was 0.000161 newtons, and the magnitude of the electric force on the floating tape was 0.001617 coulombs. Now some more experimental data. This was all of the extra parts I calculated, including the numbers of electrons lost, charge of tape, tape area, atom area. If you want a more in-depth explanation, if you go to my channel, you can see lab 1. And just to the right here, this was also the pictures of the charge tape system interacting, just to give you a little bit of visual. And my assumptions for this part of the lab was that there was no air resistance, the long piece of tape was treated as a point charge, and each piece of tape had evenly distributed charges on it. Now onto our lab 2 initial conditions. The system and constants were at the same as lab 1, meaning our length, mass, force of gravity, none of that was changing because we didn't change any of the tapes or any of the data points for lab 1. The assumptions were similar in fact there was no air resistance and the tape was said to have the same amount of charge or was evenly distributed among the length. The only real big difference was that the long piece of tape was treated as a line charge instead of a point charge. And then the surrounding system I said and assumed to have no effect on the tape's charge. Now I used the constants F, G for the force of gravity. I times mass times gravity and got this number 1.61 times 10 to the negative third newtons, which was coincidentally what I set equal to the force of the electric field because they did need to cancel each other out. And then I used this formula using the electric field of a rod to then find the force of the electric field to be 1.25 e to negative 8 coulombs. That would allow me to cancel out my force of gravity and force of the electric field in the computational model that I will show shortly. Just so you know, r was the distance between the two tapes. I found using the r vector formula as stated in the introduction, and then also L was the length of the tape. Here was the WebPython simulation. This part of the code was just constants and given values from the experiment. This part right here depicted the electric field following this formula right here. And then this is where our first difference from lab 1 was. This is how you find the lines of the charge, or like a line charge in WebPython. It was given to us in the lab, and I did not edit this part. Next, this is how you find the electric field of the line charges. Right here, this section specifically was how you find the E net, and then right below it was how you found the F net. And right here was dividing the tape into infinite pieces, or finite pieces, very small pieces, so we could do the electric field of the line charges up here. And just this code right here was printing to the cell and allowed us to create this image, which finally leaves us to our computational results. Now the charge that I used to calculate the line charge was 1.25 e to negative 8 coulombs and got us to a very close cancel out of our magnitude of electric force and gravitational force within a very small degree of difference. And the possible errors here could be the measurements not being precise during the experiment, i.e. I used a ruler in my eyes to measure the distance between the two tapes while they were floating, which isn't the best way to measure. And then there's also not taking into any environmental factors or anything outside the system. And there was also human error, as in I could have mishandled the tapes and dissipated some of their charge. Now the what if questions. For that one, my lab 1 charge estimate was 4.24 times 10 to the negative 9 coulombs, while my charge 2 estimate was 1.25 times 10 to the negative 8 coulombs. And these differ because there was a different level of precision used in the calculation, and the line charge model, which was the model used in lab 2, was more accurate because it divides the tape up into tiny pieces, and that more accurately demonstrates and calculates what's going on in the electric field, as it divides it up more efficiently. Also, thank you so much for listening today. Here are my citations, and have a lovely day.